Okay, so the recording has started. Can you see my screen?
Yes, sir.
Okay, so in today's session, we'll cover various sampling techniques that you studied in your previous lectures, sampling techniques, and then we'll empirically confirm the central limit theorem. Before this, I'll give a brief intro to plots in Python. Okay, so copy this path to follow along. We'll use this dataset link. Yeah, so copy this link. We'll access this dataset for this live session. So we will need pandas. We'll need NumPy. We'll need statistics. Yeah, we'll do this part later. So is the font okay?
Yes.
Yeah. So rather than uploading the file to Colab, we can directdirectly access it through a link if it's available on the internet. So what we do is df is equal to pd dot read csv, and you just supply this URL. Yeah. So this dataset is about various species of penguins, their habitat and their physical characteristics. That is bill, depth, gender, year, etc., etc. So we'll try to sample these and, for example, random sampling and stratified sampling based on various characteristics. So see if you can download it as well. Uh, right off the bat, we can see that it does have null values, so we can just drop them. So df is equal to df dot drop na, and then we can reset the index. Yeah, now we don't have these values, and index we have it. Okay, so the first thing is, let's say a random sample in pandas. It is very easy to do. For example, you have a data set and you want to sample out, let's say 10 rows. You just call df.sample and supply how many rows you want to sample. So it will give you this. To keep it repeatable, you can set a seed. That is, let's say seed is 7. We can set a seed for numpy, and we can also supply a random state here, so that the same 10 rows are taken every time. 304, 304, 304. Okay. So let's say, let's check the distribution of, let us say, the species in the original data set. So the way we do it is uh, df dot species value underscore counts. In case your column names are strings without any spaces, you can use it with a dot rather than doing this. Okay, so this makes it quicker to write. So let's say value underscore counts. We see that the original distribution is Delhi, Gentoo, and Chinstrap. To get a percentage rather than a count, you can pass normalize equal to true. So this gives you the proportion, that is 46% are Delhi's, 35% are Gentoos, and so on. So if we, let's say, in our sample, we have we have 333 rows. If we, let's say, pick up 50 of them and we check species once again, okay, so it comes out close but not identical. If we, let's say, supply a different seed, let's say 1, it may go down. For example, if this is 20%, 18%. Mm, if we supply, let's say, 10, 48%, 43%. So we see that it does not respect the distribution of the species when you sample randomly. Okay, so another way that you had studied in class was to do a stratified sample. Before going into that, in case, let's say, we want to sample randomly, but rather than specifying how many, we want to specify what percentage we can supply. Fraction is equal to, let's say, 20%. So it will draw 20% of the rows out of it. So maybe we can store it in a df underscore sample, or we can say, let's say, random sample, and we don't need this part. Similarly, okay, so here we have 20%, and in this case we had 50, total 50. So let's say print random sample dot shape. Here it gives 67, here it gives 50 exactly. So now here's a practice problem for you. How can you do stratified sampling in a proportionate manner? So what stratified means is that I want you to take, let's say, let's say 10% from every species. I have 3 species. Sample out, let us say, 10% from each species. Okay, can you do that? Take 10 minutes to attempt the problem. Is the problem clear? Stratified sampling. Any progress? Yeah, if anyone is done, please raise your hand. That gives me an idea. Okay, so for the others, let me maybe give you a hint. So what we are trying to do is, uh, initially when we are sampling randomly, let's say I say give me 20% of the total number of rows. Those 20% can come from any species. It will not respect the proportion of each species. The idea is that, let's say we have three species and I ask you for 20% of the total, extract 20 from each species and then combine the data set. That ensures, let's say if somebody has a very big proportion, 20% of that will also be a big proportion. If somebody has very few rows, a species has very few rows to it, 20% of that will be a small fraction. And when we combine the three together, the overall ratio among the species will be respected. I hope it makes sense. So if you have done it correctly, what will happen is when you do value underscore counts on its species, you will get exactly these numbers from the original space. Almost the same. Was anyone else able to do it? If someone has attempted it, is maybe halfway through it. You couldn't get the data set. Wait. Okay, so it's 7:25. Let's start. A naive approach would be that we can iterate over the species. Okay, so let's say in this case we have three species, Adelie and these. I can extract the rows corresponding to Adelie in a separate data set. I extract Gen2 in a separate data set and Chinstrap in a separate data set. So I get three data sets. We iterate over species, one data set per species, and then I can randomly sample 20% of the rows. Okay, and finally I can just concatenate the three and just reset the index. That would be one way to do it, but there is a shortcut method, a faster way to do it. So what we can do is we have a data set. If we, let's say, group it by the species column, okay, whenever we apply group by to a data frame, it asks us to give an aggregation function. That is, give me a function that I should apply over this grouping. That I have got all the rows, let's say to Adelie. What should I do with this? I'm asking it that, okay, now that you have got all the rows for Adelie, randomly sample, let's say 20% out of it. So usually what we do is we will apply mean function or count function, something like that. I can ask it to sample in this case. So what I will ask it is, if let's say I'm not giving it a standardized mean function, sum function, you should use apply. When you write apply, you can supply any function you want. So I'll ask it to apply a lambda function, that is lambda x. In this case, x will be a data set for every species, and I'll say, okay, from x, just sample, let's say 20% of the data, and we can set a seed like this. Okay, so if we do this, we'll see that we have Adele, we have Gentoo, and so on. So if we, let's say, save it in a strat sample, how do we name previous one? Random sample, strat sample. Okay, so we have strat sample, and we do strat sample dot species. We have species here dot value underscore counts, normalize equal to true. So 43, what did not numbers did we have? We see that the numbers are almost the same. So does anyone have any confusion with this? Is this clear? What we did here? We just did these three steps in one. Split the dataset into three, extract a fraction, combine everything together. Can I have a raise of hand in case it is clear? Okay. So one thing that you may have noticed is that if I, let's say, want to continue with this sample data set, so we have, let's say, strat sample. Now we have another index on top of the original index. We don't want that. So we can drop this by saying, let us say strat sample is equal to yeah. So I was saying we should maybe drop the original index so that we can get back to the same data set. So let's say we have a strat sample and we say, let's say drop underscore level 0. So when we group, we get actually multiple indexes and they are classified into level 0, level 1 for a multi-index data set. We can drop the original index. And then if we uh, yeah, so now we don't have that index. The only thing is that the indices, we can reset them. Okay, so we have 0, 1, 2, 3, 4, so on. Another thing is that when using, let's say, a proportionate case, we can also use a disproportionate case. In a disproportionate stratified split, so what we do is rather than extracting, let's say, a fraction from every species, we can also take out a fixed number of rows from every species. Let's say 10 rows from gen 2, 10 from this, 10 from this. Remember that it is still stratified in that I am guaranteed that I am taking the equal amount from each, but this time it's not a fraction. It is the exact number of rows from each one of them. So everything remains the same. What we do is, rather than supplying a fraction here, we can say give me 10. Okay, so we have 1/3, 1/3, 1/3. Clear? Okay. So try out a simpler problem. You have read about systematic sampling. In systematic sampling, what you do is, let us say you have n number of rows, you pick a row at random. Okay, you have to decide how many, how do I say it? You basically decide how many jumps, or basically how many splits do you want in your data set. Let's put it that way. How many splits in the data set? And then starting from this random row, you jump that many times. So let me explain it with an example. So let us say you have 1000 rows. You randomly decide to start with 7. Okay, and you also decide that you want uh, to jump from 7 to 17 and so on, to a jump of 10 every time. Okay, so once you decide that, you pick up 7, 17, 27, these number of rows the first time, and then you keep going until you get the desired number. Is that clear? Any confusion in this? No, the session is actually for implementing this. I mean, whatever you do in your weekly sessions, the idea is to put that into code. So if you're already familiar with that, you can skip. So is this clear, systematic sampling? Can you implement that? I mean, so think of it like this. That is, you decide a random number, then you decide on a jump. That is, from this random number, I will jump this many rows forward, and at equally spaced intervals, I will pick that row. That is how you do it. Sometimes you may also do that. You may sort the data set prior to doing all of this. So let us say you had, let us say, rather than species, you were doing it with, let's say, weight. So what you would do is you would sort the data set based on weight, then you pick up a random row and you do these jumps basically. Yeah, you can use anything you want. Yeah. See this if this helps. So doing it in two steps is essentially what I was saying earlier. That is, you decide on a jump. If I want my sample to be, let's say, of size 100 and I have a data set of 1000, I my jumps should be spaced by 10, 1000 by 100. Anyone done? You'll probably not need any function. Yeah, in case you have a solution, don't post it. Let everyone try.
Okay.
Yes, it is the correct solution though. So those who are done, please raise your hands. Okay, so it's 7:45. Let me show it. So initially, in our case, we know that n is the length of the data set. Let's say we want a sample of 100 rows. So we can decide on a jump, or we can just call it k, as is the lingo. So we just do an integer division by n. Okay, so we have our three parameters. Now what we want to do is begin from a random number. So start should be a random number, a random row. So the way we do it is, let's say np dot random dot uniform. We can pick a number from a uniform distribution where the low is 0, high is let's say length of the df, and yeah, that should be enough. Maybe random state. So we have the start. Now we want to begin from this start and pick a row at jump of k. So one way to do it is, as someone had posted, that you create an index and then you just do that. An easier way to do it is, let's say in Python you have a list. Let's say L is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, and I say I want elements from, let's say, the second element to the sixth element with jumps of 2. Okay, so I only get 3 and 5. It skips the one in between. So the third parameter in indexing is the jump parameter. So you can simply do df.iloc. You begin from start, you go all the way to the end, so you don't supply anything in between, and just supply k at the end. So this would be a systematic sample. df.iloc start. Oh, we need to convert this to an integer. Yeah. So if we do systematic sample dot shape, it gives us 25. So interval of 100, what was k? Print n, and k. Okay, so we had 333 rows. We decided to partition it into three parts. So we had a total of three splits. And I think we should have jumped by n rather than by this. No. And where did we start? Oh, we actually got a very big number in here. So let's say we supply a smaller start, let's say 50, and then we do this. So 95. So what it's doing is it's starting at 50, and after that it's jumping k rows ahead, picking a row, k rows ahead, picking a row till it reaches the end of the data set. Okay, so let's try another one. We have weighted sampling. So in weighted sampling, what we want to do is, let's say in our original distribution, in our original distribution, we have 40% of Adelis, Gen 2s are 35, and Chinstrap are 20%. For some reason, when I sample the data set, I want that Chinstraps should be 3 times more likely than the other two. Okay. I want to draw the rows randomly, but Chinstraps should have 3 times more chance to be sampled than these two. Can you do that? 750. Let's wait till 85. See if you can do it. Systematic sample. Yeah, just a minute. By the way, I'll post this code to the GitHub repository, so you need not take any screenshots or anything. So try to draw, let's say, in case of this, draw 20% of the total rows where chin straps are 3 times more likely than the other two species. Okay. So, Ankur, when you say efficient, do you mean speed or do you mean the quality of the sample? Okay, so here's a hint. So let's say, as before, we call, let's say, a df dot sample with a fraction of zero point 0.2. We can supply the weight of every row. Okay, so if you are able to create a row or maybe a series of weights, one per row, which instead should have a weight of 3 and the others should have a weight of 1, you will be able to draw this sample conforming to this condition. So try that. Create these weights basically and supply them to df.sample. In the given population count was in systematic. Yeah, of course, because I mean in systematic you don't respect uh, the proportion of basically every category. So for example, in case of species, systematic does not guarantee that I will have this many of these, this many of these, this many of these. So you will usually use systematic with a numeric column. So let's say you had ages and you sort your data set based on the age column, and then you can basically decide that okay, I'll do this jumps of these. If you have categorical data, let's say species, you should go with a stratified split. Is anyone done? If anyone is maybe halfway through the solution, okay, so let's start. As I indicated, the problem boils down to just creating a series of weights. We want to pass weights such that chin straps are weighted 3 times more than the others. Okay, so the way we do it is we say, let's say df dot species is equal to chin strap, if that is the correct name. Chin strap, yeah. So let's say we do this. It returns a series of true and false, a boolean series basically. Okay, so what I can do is there is a function np dot where. Okay, so what np dot where does is, given a condition, you can set specific values. That is, if the condition is true, set x, otherwise set y. Okay, so let's say I say my condition is that the species should be chin strap. Okay, then I say that weights is np dot where my condition. In case I am a chin strap, I should get a weight of 3, otherwise I should get a weight of 1. So let's say we print this. Wherever the condition was false, we set it to 1. Wherever the condition is true, it is set to 3. Okay, so now we have these weights, we can just pass them here. So we get this. So let's say we do species dot value underscore counts normalize is equal to true. We see that chin straps are actually the most dominant species now, while as in the original distribution, Adelis were the most dominant species. That happens because we have given them 3 times more weight than the other two. So does this make sense? Derived species Adelis, sample from them 13, derived species sample 13. Um, I mean, in this case, I won't say, I mean, that we have set it, it is thrice more likely. I am hard coding the values. That is, give me these many of this, these many of this, these many of this. A simpler way can also be that, let's say we decide that we want to take out, let's say 100 rows, and we say that 60 of them should be from chin straps, and the rest, let's say 40%, 20 from this, 20 from this. That would also be another solution. But I think this may be the, I mean, the most efficient one, maybe. Another thing that you can do is you can create an additional column in your data frame by the name of, let's say, weights. And you can iterate and just say, if I am a chin strap, set my weight to 3, or otherwise set my weight to 1. Then you can sample based on that. And at the end, you can drop the weight call. That would be another solution. Does anyone have any confusion? Okay, so the last form of sampling is, let's say, cluster sampling. In our data frame, we have got the body mass in grams. Okay, so what we want to do is we want to create, let's say, 10 clusters within body mass, and then I want to sample from the first, third, and fifth cluster only. So the way you can cluster is maybe you can just divide it into quartiles. So normally quartiles are just 4, so you can build 10 quantiles. So the 0th quantile is that much, and first quantile, second quantile, and so on. And finally, we want to draw samples from the first, the third, and the fifth only. Okay, so can you do that? We could create clusters based on any condition. This is the easiest way. That is, we just create that as quantiles, 10% data, 10% data, 10% data. In reality, you may have different clusters. So it's 8, 8. Let's wait till, how much is that? 825. Try this one. Any updates? It is not that difficult. You can add, let's say, here's a hint. So you can add a column by the name of, let's say, bins, and for every row you assign a bin to it. That is, you are bin 1, bin 2, bin 3, and so on. Then you extract rows corresponding to these three bins. So you have a reduced data set now. Then you just reapply stratified sampling as we had done earlier. Okay. You can again use group by and apply. So the main part is creating 10 bins and then just extracting three from them. You can use pd.cut to create bins. What pd.cut does, you supply it maybe a series and it will create as many columns as you want. So let's say I supply df dot body mass g and I say 10, it will give me 10 bins. So try that. Yeah, does anyone have a doubt? Yeah, Utkarsh, go ahead. Okay, so let's start. So we need 10 clusters, and we have decided to do it on body mass. So we say, let us say clusters is equal to df dot body mass g, and we apply pd dot cut to this, and we say I want 10 bins. So let's see what does it return. So it returns these clusters, that the first cluster is from weight this to this, the second is this to this, the third is this to this. I am only interested in these values. So to get that, you set label to false. It says labels to false. Okay. So you set labels to false. So what you get is, you get that the first row is cluster 2, the second is cluster 3, cluster 1, and so on. Then we decided that we'll only work with 1, 3, and 5 clusters. So let's say we have chosen clusters. They are 1, 3, 3, and 5. So what we can do is, clusters is this. We can say df underscore chosen is equal to df. Yeah, in fact, let's append maybe a column. So we have df dot clusters is equal to clusters, this one, and then we can say df df dot clusters dot, in fact, clusters is in chosen clusters. So how many should we get here? So let's save it. So df underscore chosen is equal to this. So if we look at its shape, So we have a reduced data set that is 130. Now in this reduced data set, all we have to do is take a stratified sample based on the clusters column. Remember that now we have an additional column of clusters. Here, clusters. Okay. So what we do is same as last time. So we say df underscore chosen dot group by. We want to group based on clusters. Then on every cluster, I want to apply a function. What is that function? That is given those rows, sample out, let's say 20% with random state set to seed, and we can say that these are my, let's say, sample underscore cluster. Now we know from last time that this adds a level, so we can drop level 0. So if we take a look at this, so did it run? Yeah. So sample cluster, we have these clusters. Now again, we can just reindex this, reset underscore index, drop is equal to true, and we get our clusters. So any confusion? Yeah, you can also see that we have only 1, 3, and 5, right? Now once I have done that, I can also drop these. That is drop clusters from the original as well as this one. So let's say df dot drop clusters x's is equal to 1, in place is equal to true, and same for this one. Sample cluster dot drop cluster x's is 1, in place is true. Hmm. So we're doing it twice, so that's why it's throwing an error. So does anyone have any confusion with this? Very straightforward. So can you raise your hand if it's clear? Okay, so now we're done with the sampling technique. So we covered a random sample, a stratified sample, a systematic sample, a weighted sample, and finally a clustered sample. So the last part is to verify the central limit theorem, empirically verify. Yeah. So before that, I said that, what is the time? Yeah, 8:27. So let's say in Python you want to plot something. So let me give you a very brief idea of how to do that. So you'll use this library whenever you plot, matplotlib. Okay. So what you want is from, you say import matplotlib.pyplot as plt. So this is the part that you use for making all the plots. People may also use Seaborn as SNS. Seaborn is built on top of Matplotlib. It is just more aesthetic and it has better functionality than this one. But in any case, people will use these two in conjunction. You rarely do people use Seaborn alone. Okay, so you do this and you create an environment for creating your plots. Afterwards, let's say you want to create something for, let's say for, we have some x values. So we say, let's say np dot linspace. I set values from, let's say 0 to 10. I want 100 values. So what this is doing is it's just giving me 100 values starting from 0 ending at 10. And I, let's say, have a corresponding values that is, let's say, square of x, and I want to plot this function. So the way you do it is you first create a figure, that is, you say plt dot figure, and you specify a fig size. So in this case, let's say I'll say an 8 by 4. Okay. Once you have a figure, everything you write afterwards until you either save the figure or show the figure, it will be drawn on this figure. Okay. So what you do is you say plt dot plot, you supply x, you supply y. Okay. and then you say, let's say plt.show. Okay, so we see this function, it's going from 0 all the way up to 10. Notice that I did not supply these values, that is where you should start the x-axis, where you should end the y-axis. It does that automatically. Now there is a way to control that. Okay, so let's say you have plt.plot this, but you want to specify, okay, I don't want values from 0 to 10, I want them from, let's say, minus 10 to 10. So what you say is plt.xlim, you say start from minus 10, end at 10. And then if you run it, it starts from minus 10, ends at 10. Now, because we only had values from 0 to 10, we don't have any plot on this side. Okay. Similarly, we can extend the control the y-axis as well. Does anyone have any confusion up to this part? Everyone following? Okay. So now let us say that in this limit, I don't want my grid values to be at this 2.5, 7.5. I want them to be at integer values. So these are called ticks. Okay. So you can control these as well. So the way you do it is you say, let's say plt dot x ticks, and then you have to specify every value of the tick. So what I can say is, let's say, give me let us say np dot range. I go from minus 10, I go to 11 with a space of 1. So see, we have minus 10, 9, 8, 7, 6, and the grids are automatically adjusted. So I have specified that these should be integer values rather than automatic values. So similarly, you can also change this fixed size to control all of these. So yeah, okay. So let's say we have these. If you attended the previous sessions, we had covered SNS dot hisplot, SNS dot displot, and let us say PLT dot hist. So we had covered those in the last lecture, I believe. So let me show you this part once again. So what SNS dot histplot does is you specify, if you give it, let's say, a list of random values, it will automatically bin them into various histograms so you can visualize the distribution. So let us say I have a, let us say, an exponential distribution, stats dot exponential, let us say specify it to 4. So this is my distribution. I take out, let us say, 1000 random values out of this. Okay, and I want to plot them in this case. So yeah, so let's say I have these random values. What I can do is just call SNS dot histplot, give it the random values, and it will generate this, basically these individual bars, the distribution itself. So I can now visualize that, okay, this is an exponential distribution. Let's say I did not show you this particular line and I just gave you this list of numbers. By visualizing them, you get an idea that, okay, this may be an exponential distribution. Manish, can you please mute yourself? You are again and again unmuted. Yeah, so notice that these bars indicate the count. So let's say I don't want counts, I want the density or the probability. So what you can do is you can specify the stat. That is, I want this curvature to be the density plot. If you have read that, we have these probability density, probability mass. So now this becomes the probability density function. It looks the same, but the values, basically these have changed. Okay. So does anyone have any confusion with this? A his plot? No? Okay. So now let's say, rather than having random variables, I want to plot a known distribution. Okay, so let's say I want to plot a normal distribution. So one way to do it is I can again take random variables, that is stats dot norm, loc 0, scale is, let's say, 1, and I take out 1000 random variables, and I just call SNS dot, in this case, let's say KDE block. So it gives me this curve, but you will notice that it is not a smooth curve. As we had discussed in the last lecture, this happens because we are not guaranteed that these random variables are equally spaced. So we don't get a smooth curve for this. So a better way to do it is you create a normal distribution and you yourself supply the x values. That is, let's say x is equal to np dot linspace, and I ask it for, let's say, -4 to 4, 100 values, and I get the values by passing it through the distribution. So let's say norm dot pdf, I can pass it through this, and I just call plt dot plot. I give it x, I give it y. Mm. So this time we get a smooth curve. Okay. So it is better to use this when you are creating a known distribution, and let's say you have random variables. It is best to use a hist plot with, let's say, stat equal to density. So can you, using these two, okay, these two visualizations, can you empirically verify the central limit theorem? Okay, so what does the central limit theorem say? It says that take any distribution, uniform, exponential, anyone. If you take multiple samples out of it, and each sample is of a decent size, let's say 50, 60, okay, each sample is of a decent size, the distribution of their means, of the sample means, let's say sample 1 has a particular mean, sample 2 has a particular mean, of the sample means, this follows a Gaussian distribution. And if you standardize the mean distribution, it becomes a standard normal distribution. So we have the mathematical proof for it. Can you can you prove this empirically? That is, can you draw these plots and then say that it is, that indeed it is following a Gaussian distribution or a normal distribution post standardization using these plots? Can you try that? It is 8:36, so maybe we can wait till 8:50, 8:45. I'll show you afterwards. Okay, so it's 8:45. Has anyone done it? Okay, so let's start. So let's go ahead with an exponential again. So we have stats dot exponential with the parameter 4, and let us visualize it right away. So we have sns dot a hist plot. We supplied some random variables. So let's say we have dis dot rbs. We give it 1000 random variables to plot. Let's see what we get. Yeah, so this is the distribution. Now we want this to be a density, so we'll say stat is equal to density. We can set the title, that is, this is exponential PDF. Okay, yeah. So now what we want to do, we want to take multiple samples, each of a decent size, and gather their means. So let us say we decide that we'll take a total of 1000 samples. Every sample will be of size 50, and we'll have a list for sample means. Right now it is empty. So let's iterate over our distribution this many times. So for I in, do we have random variables? No. So for I in range, number of samples, we want to take a sample out of the distribution, out of this distribution DST. So we say my sample is distribution dot random variables. I want this many out of it. So sample size, save the mean in sample dot means. So sample underscore means dot append sample dot mean. So let's say we do this, we get our distribution of sample means. Okay, so now what do we want? We want to plot these the same way we did it with this. So we'll say sns dot histplot sample underscore means, and we see that it resembles a Gaussian distribution. Okay, so to confirm, what we can do is we can create a Gaussian distribution having the same parameters as the mean and standard deviation of these guys. So let's say we have mean is equal to sample underscore means dot mean, and we say std is equal to sample underscore means dot std. Now because this is a sample, we should apply Bezel's correction. So what Bezel's correction says is that when computing the standard deviation, you should divide by n minus 1 rather than n. So to do that, we can say that std is, in our case, n is equal to length of sample underscore means. So we'll say np dot sqrt multiplied by n and divided by n minus 1. So it essentially says get your when you compute the standard deviation, divide by n minus 1. So we have our standard deviation. Then what we can do is list doesn't have any mean. Okay, so we should convert it to a numpy array. Yeah, so we have n and we have standard deviation. Now we can again say, okay, give me x as np dot linspace from, let's say, 4 to 5, or maybe let's say 4.5 to 6. Let's say, for example, 4 to 6. We'll take 100 values and we'll create a normal distribution using these values, this std and this mean. So let's call them sample mean and sample std. Okay, so we have this, we have stats dot norm. We set the location to the sample mean and the scale to be the sample standard deviation. And if we plot this, let's say we have norm dot pdf and we supply x to it, and then we plot x, y, and in this case we want this to be density. Yeah, to maybe give it a color. We see that it almost exactly follows the Gaussian distribution. So is this clear? Does anyone have any confusion? Can you raise your hand if this is clear? Okay, so the last part is the standardization part. This is the standardization says if this distribution of means, this thing, if it is standardized, it follows the standard normal distribution. So to do that, let's say we have sample means. All we have to do is subtract the mean of this thing, that is sample underscore means dot mean, subtract the mean, and in fact we have stored that. So we can say sample underscore mean and divide by the standard deviation, sample underscore std. So now we have standardized our distribution. And if we plot it after this, so let's say we repeat this part, and this time in the normal distribution I can hard code 0 and 1 because I know it would be a standard distribution. So let's say we plot it from -3 to 3. We see that it follows a standard normal distribution, mean 0, standard deviation 1. Is this clear? So do you have a question or are you raising it up with that? Okay, so we'll end the session with that. Lastly, I'll upload the code to this GitHub repository. So this one. The previous two sessions are also there. So after a while, I'll upload it to this repo. So let me share the link. The recording for this session, you will find it. I think it's here as well. Yeah, this. So you'll find the recordings in this playlist. Okay, so if no one has any doubts, I'll end the session. Okay. See you next week.